Hello everybody, welcome to another episode of Math-321 Abstract Algebra. So today we are doing Investigation 24, which is the dihedral groups. Let's get right into it. Okay, so here are the focus questions for this investigation. How can we describe the symmetries of a regular polygon? What similarities do all such sets of symmetries have? What are the dihedral groups and what are some of their important properties? What are generators and relations, and how can they be used to describe a group structure? What is a presentation of a group? So I think we'll get through the first two today, and the last one will be for next time. Okay, so first I want to remind you of Investigation 19. In that investigation, we investigated the symmetries of an equilateral triangle. And I believe you guys on the board during that investigation actually made the operation table, which I've shown you on the bottom right corner here. So I hope you remember that we named that group D3, the symmetries of an equilateral triangle, that group of 6 elements, that is called D3. And so I've shown all of the 6 elements for you at the right here. So it's these 6 symmetries. You have the identity symmetry, which does nothing. You have capital R1, that is rotation by 120 degrees counterclockwise. Rotation R2, it's rotation counterclockwise by 240 degrees. Little r1, that is reflection over the axis joining vertex 1 to the center of the triangle. Little r2 is reflection over the axis joining vertex 2 to the center of the triangle. And then little r3 is reflection over the axis joining the vertex 3 to the center of the triangle. Okay. So now we have preview activity 24.1, and so here I've just reproduced the 6 elements of D3 and the operation table, and I'd like you to pause the video and go ahead and give this one a try, and when you're done, we'll do it together. Okay, so let's go over the answers here. So the first question is, use the operation table to determine if each of the following is a rotation or a reflection in D3. First is the composition of 2 rotations. So our rotations are R1 and R2, which I'm just circling here. And so if we compose those 2 elements, the region that is their composition is right here in the table. Now you can also think of I as actually being a rotation as well, because if you rotate 360 degrees, that will actually give you the identity again. So the identity is a rotation. It's like a degenerate rotation. So these areas at the table are compositions of rotations as well. And if you look at those 4 areas there in the table that I've circled, you can see that you only have R1, R2, and I. So that tells you that whenever you compose 2 rotations, you get another rotation. Which should make sense to you. I mean, if you rotate and then you keep rotating some more, or you rotate back, that's the same as another rotation. Okay, now on the other hand, the composition of a rotation and a reflection. So let me see, if I'm composing a rotation and a reflection, let me see if I can circle the parts of the table that are like that. So there's this one, there's this one, there's this part, and there's this part. Okay, I believe those are all the parts where one of the operations is a rotation and the other one is a reflection. So just, that's for part 2 there. So I think what you can see is that you're always getting reflections out of that. So whenever you compose a rotation and a reflection, you get a reflection. So that's interesting. And then the composition of 2 reflections. Let me see if I can get another color here. So if we compose 2 reflections, I think this is the final part of the table, the middle part here in green. And what you can see is that you're getting a rotation. So that's interesting. Okay, let's move to the next part. Okay, so part B, I put really small. I'm not sure if I'm going to have enough room for it all or not. So which elements in D3 can be written in the form R1 to the I times big R1 to the J, where I and j are integers. And what I want you to note here is that even though we're writing this operation as multiplication, keep in mind that what it really is function composition. So for example, what they mean by R1 times big R1 is R1 composed with big R1. And then, for example, r1 squared, that really means r1 composed with r1. Okay. And keep in mind also that when you're doing function composition, the first function that's applied is the one that's on the right, because that's what would be closest to the input. Okay, so let's see if we can figure this out. So, So I think it's obvious that little r1 equals r1 to the I, big r1 to the j, for I equals 1, and j equals 0. So if I do any of these symmetries to the 0, that just gives me the identity. And then obviously the same way for big R1, that'll give me I equals 0 and j equals 1. But what about the others? So for example, if I look at little r2, so little r2, what happens when I actually apply little r2? So I start with my triangle, the way it was labeled originally was like this, 1, 2, 3. And then when I apply little r2, what happens to my triangle? Where do the numbers go to? So I'm looking at little r2, I think what happens is I have 3, 1, and then 2 stays in the same place. So the question is there a way to achieve that by first applying big R1, that rotation, and then by applying the little r1 reflection? So let me think about this. So if I start with 1, 2, 3, like this, where could I then go? Okay, let me think for a second. So I think if I apply big R1 once, that's going to take me to, let's see, so they all move forward 1, so this will be 1, 2, 3, or counterclockwise 1 rather. And then if I actually do little r1 at that point, that reflection over the vertical line, that will actually give me what I'm looking for, which is 3, 2, 1. Do you guys see that? So that actually ends up with the same result as r2. So what that tells me is that r2 equals little r1, big R1. And remember, the one that's on the right is the one that's applied first. So in this case, it's I equals 1, j equals 1. Okay? Let's try doing another one. I think I'm going to have to erase this slide and do it again. Let's try and see if we can get some of the others the same way. Get my eraser out. Where's my eraser? Oh. Okay, so let's go ahead and see if we can do R3 now. So R3, so what is the result of R3? So when I start out, I have 1, 2, 3, and then when I apply R3, where do these go to? So little r3, okay, so they're going to be like this, 1, 2, and 3. And then so what I want to know is, can I achieve that by first doing a rotation and by then doing that reflection across the vertical line? Can I achieve the same result? Okay, so let's see. So what I'd really like to do is rotate clockwise and get the 2 back up at the top, but I think I can't do that, so I'm going to have to do big R1 twice. So this is going to send 1, 2, 3, and then let me try doing it again. So if I do R1 again, it's counterclockwise rotation again, so this is going to be 1, 2, 3, and now you see I'm only off by that vertical reflection. So now I'm going to do little r1, and I'm going to get 1, 3, 2. Okay, which is where I wanted to end up at, because that's the same as what happens after I apply R3. So what this tells me is that little r3 is the same as doing, so first I do r1 twice, and then I do little r1 at the end. Okay, let's try doing one more, and then I'll have to erase the slide again, I guess. So now I'm going to try to do R2. Actually, for R2, I think it ought to be quite clear how you do it, right? Like you just do R1 twice. So let me just show you that. So the result of R2 rotating 240 degrees, let's see, that's going to put this here 1, and then 2, and then 3. And that is the same as if we start here with 1, 2, 3, and then we do R1, big R1 once. So 1, 2, 3, and then do big R1 again. So 1, 2, 3. Okay, so big R2 equals R1 squared. Okay, and then finally, how do we do the identity? I hope it's clear to you that to do the identity, you just need to do R1 3 times. If you do it 3 times, you'll come back to where you started at. Okay, so that gives us all 6 different elements written in this particular form, where we have little r1 to the I and big R1 to the j. Okay, so now let's look at part C. So if t is an integer, can big R1 to the t, little r1, be written in the form little r1, big R1 to the j for some integer j? If yes, for which j? So this is an interesting question. It's basically asking if you reflect first and then rotate a bunch, can you achieve the same effect by rotating a bunch and then reflecting? Well, yeah, of course you can. You just have to kind of work out how to do it. So let's try maybe doing an example. So for example, let's just say t is 2. So we're looking at r1 squared little r1. So what does that transformation actually look like? So we start with the original triangle, 1, 2, 3, and then first we apply little r1, which is reflection over the vertical line. So this is 3, 2, and then we apply the counterclockwise 120-degree rotation twice. So this is going to give us, let's see, 1, 3, 2, and then we do it again. So counterclockwise rotation again, this is going to be 2, 1, 3. Okay, so now the question is, could we have achieved that by doing the rotations first and the reflection last? Yeah, I certainly think we could have, so let's give it a try. So let's do, starting point is 1, 2, 3, and let's try giving it 1 rotation. Let's see where that takes us. So this will be 1, 2, 3, and then I think if I do the reflection across the vertical line at this point, I'll be done. So this will be little r1, and this will be 3, 2, 1, which is what I wanted. That's the same result. So what we found here is that big R1 squared little r1 is the same as, let's see, sorry, I'm getting my first and last application thing mixed up. So first we did that one and then we did that one. Okay, so these two are the same. That's just one example, but I think you can work it out for other examples and you might find some pattern, which we're going to learn about a little later. Okay, so let's go ahead and do the last part of the activity here. So we're going to define little r as little r1 and big R as big R1, and they want us to rewrite the operation table so that every element is in the form little r to the I, big R to the j for some ij. So I just wrote down the results of the last parts of the activity. So what we've got so far is that little r1, that's little r1, so that's just going to be little r. Big R1 didn't need to be rewritten, so we just left that as big R1. So that's going to be big R. And then we found that little r2 was little r1, big R1. So that's going to be little r, big R. And then r3 we found was little r1, big R1 squared. So that's little r, big R squared. And then, oh, excuse me. Okay. And then big R2, oh, big R2 was big R1 squared, so that'll be big R squared. And then finally, the identity element was big R1 cubed, which is big R cubed. Okay, so if you want to rewrite this table, you can do it with those substitutions. I think I'm not going to actually, do it, but those are the substitutions that you would make. Okay, so introduction to this investigation. So what we're going to do in this investigation is we're going to discuss the symmetries of a regular n-gon. So what is a regular n-gon? That is simply a polygon that has n sides, and the regular part means that all the sides and angles are the same size. So what I want you to think about is the fact that a regular n-gon will always have two n symmetries. So half of the symmetries, n of them, will be reflections, and then the other half, the other n, will be rotations. So let's look at some examples here to think about that. So there's a slight difference between when n is odd and when n is even in terms of the reflections. So when n is odd, you can take each vertex, like in this triangle here, and you can just connect them to the center point, and then those will be your axes of reflection, and you can see there will be n of them. On the other hand, when n is even, the reflections are a little bit different, because if you just take each vertex and connect it to the center, you don't get n different lines, because they go all the way through, right? So they go all the way through. So you would only get half of the axes of reflection that way, and then the other half are going to come from connecting the center points of each side. And the center points of each side also make axes of rotation for when n is odd. They just, if you go through, you go all the way like that, and you get back to another vertex. Okay, so those are the reflections, and then for the rotations, we define this quantity, this angle called theta, which is 2 pi over n. So in other words, that's 1/nth of the way around the circle. So when your polygon has n sides, then rotating it by 1/nth of the way around the circle, that's the smallest of the rotations for the symmetries. So the different angles for the rotations are going to be 0, first of all, that's the identity. You can also get the identity by going all the way around. And then theta itself, and then 2 theta, 3 theta, and so on and so forth up through n-1 theta. Then if you would go all the way to n theta, that would be all the way around the circle, so that would be the identity again. And then all of those rotations are performed counterclockwise. A clockwise rotation is also a symmetry of the n-gon. It's just that you can get the clockwise ones from the counterclockwise ones. Okay, so that is the symmetries of a regular n-gon. And now let's talk about the dihedral group. So definition 24.2, let n be an integer with n greater than or equal to 3. The dihedral group of order 2n is the group of symmetries of a regular n-gon. Okay, so we just call that group of symmetries that we just talked about, it's called the dihedral group. And then obviously you need n to be greater than or equal to 3, because if it's any smaller than that, then you don't have a polygon. A little caution here is that there's some different terminology floating around out there in different textbooks and authors. So some people call the dihedral group of order 2n by the name D2n. So just make sure if you're reading about this in some other place like Wikipedia, make sure you know what they're talking about. Okay, and now let's talk about relationships between elements in Dn, the dihedral group. So what we're going to try to do is extend the ideas in that activity 24.1 that we just did in such a way that we can efficiently represent all of the elements of Dn in terms of just two elements, little r and big R. So first we're going to need to have a really consistent notation so that we know what we're talking about. So let's call the rotations of Dn by the names R0, R1, R2, all the way up through Rn-1. And then what those names will stand for is for each R sub I, that will be a counterclockwise rotation by the angle I theta, where theta is 2 pi over n. Okay, so R0 is staying in place, you're not rotating at all. R1, you're rotating by theta once. R2, you're rotating by theta twice, so on and so forth. And then we're going to call capital R to be capital R1. And what I want you to notice is that all of the rotations are generated by that capital R, that R1, where you just do the theta rotation once. So in other words, by generated, I mean that all the powers of capital R give you all of the different rotations. Okay, so for example, R0, that's R to the 0, R1 is R, R2 is R squared, R3 is R cubed, and so on and so forth. So in other words, what we can say is that the group generated by R is all of those n rotations. And then that also means, you remember the definition of the order of an element is the size of that group that it generates. So the order of capital R is n. And then notice also that because capital R to the n is the identity, so it's going all the way around the circle, if at any point you need to simplify something, it might be useful to be able to multiply by Rn wherever you want to do that at. Now for little r, assume that we've drawn the regular n-gon in such a way that vertex 1 and the center of the polygon are both on the y-axis. So for example, we could have like 1 is here, and then we have the rest of the triangle is like this. Okay, so this is the center here. Something like that. Then little r is just going to be the reflection across the y-axis, the side-to-side reflection, like that. Okay? So it's the same as the little r that we were doing in that activity before. Okay, so with all that notation established, let's try to answer the following questions. Go ahead and pause it and try this for yourself, and then we will go over the answers. Okay, let's go over the answers here. So first of all, what is the order of little r and why? So remember, what is meant by the order of an element is actually the number of elements that are in the subgroup generated by that element. And what I mean by the subgroup generated by that element is the following: all the different powers of that element for any integer power. So what are the different powers that we get from r? So there's r itself, of course. What about r squared? So if you square r, you're doing the reflection twice. That's actually just the identity. And then if you think about it, if you do the reflection 3 times, that's the same as doing it once. If you do it 4 times, that's the identity again. So no matter how many times you do the reflection, there's only these 2 possibilities, these 2 elements. So the order of r is 2. Okay, part B, explain why capital R to the I is not equal to little r. Well, I think the best, easiest way to explain it is capital R to the I is a rotation, and little r is a reflection. And reflections are not rotations. They're just not the same. Yeah, you can like multiply them together and get different things, but a rotation itself is not going to be a reflection. Okay. So part C, now explain why little r times big R to the I does not equal little r times big R to the j for any ij between 0 and n except when I equals j. Okay, so let's think about this. So remember, the dihedral group is a group. So suppose that we did have little r times big R to the I equals little r times big R to the j. Then we would be able to do cancellation. So we would have that big R to the I equals big R to the j. Okay? So if we have that I and j are in this restricted range here, between 0 inclusive and n not inclusive, and we have that I does not equal j, then big R to the I and big R to the j are 2 different reflections. You can have values of I and j that would be different, that would give you the same rotation, but not in that restricted small range. So for example, you can always add n to any of the exponents and you'll get the same rotation, because that would just be adding another trip around the circle 360 degrees. But because you have this little inequality here, that's not possible. Okay, explain why we can write all the elements of the dihedral group as I, r squared, r cubed, dot dot dot, should be a comma here, up through r to the n minus 1, and then little r, big R squared, dot dot dot, up through little r, big R to the n minus 1. Okay, so I think this is coming from parts B and part C. So it's relying on those. So little r cannot be written as a power of big R, and powers of big R are unique in the range, at least in that restricted range that we talked about, where it starts at 0 and then goes up to n minus 1. So all these elements must be distinct from each other. None of them can be the same. And since they're all products of little r and big R, they must all be in the dihedral group. Okay, so since they're all distinct and they're all in the dihedral group, and since there are 2n of them, this must be the dihedral group. Kind of running out of room here. This is Dn. Okay, so let's talk about simplifying elements of Dn. So if we want to be able to completely simplify any combination of little r and big R, all we really need to do is to know how to translate between these two forms right here. And so let me show you an example of how you can figure out how to do this when I is 1. So we're starting with big R times little r. So first of all, we can say that big R times little r is big R little r inverse. And that's because big R times little r is a reflection. And we know it's a reflection because remember that we found that all compositions of rotations and reflections are reflections. And also, I mean, you can just look up exactly what big R little r is in the operation table and find that it's a reflection. So anyway, all reflections are their own inverses, so that's how we get this first equation here. And then next one is moving from the fact that we have big R little r inverse. We can distribute the inverse to each element, and then we also have to swap the order. That order swapping thing, that's just the rules of inverses in groups. You remember that hopefully from matrices, and we also proved that that's true for groups as well. When you distribute the inverse, you have to swap the order. And then finally, the last one here, we can just replace our little r inverse with little r, because r is a reflection and all reflections are their own inverses. Okay, so we've simplified all the way from big R little r to little r big R inverse. Okay, so let's look at this activity. So we just learned that big R little r is equal to little r times big R inverse. So this is basically telling you that if you want to swap the order of big R and little r, you're allowed to swap, but you have to put an inverse on the big R. So now let's try to extend this concept to the rest of all the combinations of rotations of big R to the I times little r. So go ahead and try this activity here, see how far you get, and then we will go over it. Okay, let's go over this part A. So we're using the fact that big R little r equals little r big R inverse to explain why big R squared times little r equals little r times big R to the negative 2. Okay, so let's see if we can break this down. So I'm going to start with the left-hand side of the equation that I'm trying to prove. So I'm going to start with big R squared times little r. And then what I want to do is try to slowly move through some steps and end up with the right-hand side over here. Okay, so let me apply what I know. I think I can separate this into big R times little r. So if I break off that big R times little r part like that, I can substitute from up here and replace that with little r, big R inverse. Okay, let's see. So now I've got the little r in the middle. Okay, let me try separating again and putting this big R and this little r together. So I'm just using the associative properties of multiplication, or rather of function composition. Okay, and so now I'm going to apply this again right here. So this is going to be little r, big R inverse, big R inverse. Okay, and now I can just combine, I can drop the parentheses and combine these two big R's to the -1. Remember, if you have the same base or the same element, you can combine their powers. This. Okay, so we did it. Okay, so for part B, we're going to try to do the same thing. So assume that big R to the I times little r equals little r times big R to the -I for some I greater than or equal to 1. And then we're going to try to show this other equation. So I'm going to again start with the left-hand side, and I'll try to work my way towards getting the right-hand side. Okay, so I'm going to try to apply this equation right here. So I think what I want to do is like break off a chunk that looks exactly like this part. Okay, so let me try to do that. So big R, and then this will be big R to the 1, and then this will be big R to the I. Okay, and then little r. And so I'm just gonna put that into like one chunk there. This part is kind of unnecessary, but at this point then I want to substitute here, here. So this will be big R times little r, big R to the -I. Okay, and then what can I do? So I think I can do a different chunk again, just like last time. I can do big R, little r, I. Okay, and then I still know from the last slide that this is going to be little r, big R inverse, big R to the -I. Okay, and then I can drop my parentheses, and I can combine the exponents on big R to get -1 minus I, which is actually the same as -I plus 1. Okay. Part C, explain how we have shown that big R to the I times little r equals little r times big R to the -I for all positive integers I. This is very simple. What we actually did was a proof by induction. Okay, simplifying elements of Dn. So now that we know that equation that we had just proven, we can compute every possible product in Dn really efficiently without needing to draw any polygons at all. You guys remember how hard it was to compute those products with drawing polygons? And I gave you that extra credit problem too, where you had to fill it in using kind of Sudoku method, but even that Sudoku method is not going to speed you up that much because you need a lot of it to be done before you can use it. So this, what we've learned, this equation right here, and the fact that we can represent every element in the form of little r times big R to some powers, this completely lets us compute things in the dihedral group very quickly. So let's just look at this example here. I have little r big R cubed, little r big R squared. And so what I can do is just kind of rearrange the parentheses to how I want them, to have big R cubed times little r be the part that I'm focusing on. And then according to that equation that we just proved by induction, I'm allowed to swap the order, but I have to put a negative when I do that. So then I have a negative there, and then I can sort of reorder the chunks, use the associative law there. And then r times r is a reflection, so this gives me I right here. And then I can just combine these two powers of big R to get -1. And now to finish up, because I was looking for getting a positive power down here, what I did was just replace the identity with big R to the n. That's not like a necessary step, but if you did want to end up with a positive exponent, you could do that. Or you could just stop right here with R inverse. Okay, The last topic of this investigation is generators and group presentations, and I'm just going to tell you a definition and we'll leave it at that, and then we'll talk about group presentations next time. So you might have noticed that the dihedral groups are kind of similar to a cyclic group in the following sense. So in a cyclic group, if we have G being the cyclic group generated by A, that means that G equals A to the n for all integer powers n. And so that means every element can be written as a power of the generator A. And then in a dihedral group, it's kind of similar, right? Except we don't just have one element, we have two elements, little r and big R. But we can use just little r and big R to write every single other element. So in other words, you can define the dihedral group like this. It's little r to the I, big R to the j, where I and j are integers. So that's kind of interesting. And because of that, we have this definition here. A subset S of a group G generates G if every element in G can be written as a finite product of the elements of S, or a finite sum if the group operation is written additively. And then the elements of S are called the generators of G. So for example, little r and big R generate the dihedral group. And those are the generators of the dihedral group. Okay, everybody, I'm going to leave it there, and we'll pick up next time with the rest of it. So thanks for watching. If you guys have any questions or you need any help on your homework or anything, just send me an email. We can do a video chat, or we can just email about it. So I think I may have forgotten to mention, but I'm hoping that you can just turn in all your homeworks by email from now on. Just email me the PDFs. And if you want to correct some homework that I had already graded, it will be very helpful if you could send me photos or scans of the marks that I had put on your old homework, so that then I can see how many points I need to give back to you and what I had taken the points off for. And all right, thanks everybody. See you next time.